last week we started by explaining the importance of energy auditing in carrying out design process for solar energy systems. And basically, it's not only for solar energy system. I've explained to you, it can be most times when you are sizing equipment, you need to carry out energy audit to be able to know what requirements the system you are designing or the equipment you are trying to provide for the client is going to take in terms of capacity. So, and I believe we have extensively talked about that. So let's just move straight to the point. So Abib, or I don't know, the person in charge of the social media on LinkedIn, posted the table that we talked about last week. And I said that today we'll try and see how to put in some additional information into that table, which is the power factor, the surge. And I'm going to explain how this comes to be when it comes to designing. I also want to clear this notion that solar energy is only for engineering students. That is wrong. And I appreciate the composition of the Energy Club because it consists of engineering students, some students from law. This is beautiful because everyone of solar energy takes virtually many disciplines: finance, law, engineering, civil. So this is a good place to be. So if you are not doing electrical engineering, so don't think, oh, maybe this class will be so difficult for me. I bet you it will not, because I am trying to do as what I can do to break this down to ensure that everybody is carried along. And that is my take for this class. And I want you to put your mind to it. What you just need is tenacity, the ability to put into practice whatever I have explained to you. You can also do more research, go on YouTube, though not every information on YouTube is correct, but you can get a lot of information there. By the time you look at 10, you will be able to know which one is actually right for you. So let me share my screen to share some information to drive home our point based on the table we discussed about last week. I believe you can all see my screen now. If you can't see it, let me know. I believe you should all be able to see it now. And is it visible for everyone, or is tiny at your end? If you can see it clearly, that's very good if you can see it clearly. Okay, beautiful. So I have two Excel sheets in here. So I'm going to talk about the first one before I move to the second one. Now let's look at the first one. So this is a typical of what I explained last week. So everything we are doing, we can actually represent it. We can type it into an Excel sheet. So let me just run through this. We have load, we have the power need, which is the wattage. We have quantity here. We have the total power need. We have the daily usage. Now, this daily usage was not included last week. So I have the daily usage here, and I have the daily energy here. The daily energy is the product of the what? Of the total power need, which is in wattage, multiplied by the daily hours of use. You guys will see that this table is very simple. It's just you doing multiplication of this and this together. So there's no big deal, really. It's just for us to put all our heart to this and see how it goes. So I take number one, CFL light bulb. The power consumption was taken to be 20 here, and we have the quantity, which is the number, to be 10. So the total power need will be 20 in 10 places, which is 20 times 10, which is 200. Now imagine I'm going to put on this light bulb for 8 hours, 8 hours, 8 hours, 8 hours. So I have 200 multiplied by 8. If you can see from the formula here, you can see that is the product of the total power, which is 200 multiplied by 8, and that gives us 1,600. And this 1,600 is the daily energy. Daily energy, as we can see now, we have 1,600. 1,600. Okay, so this white 1,600, as you have it here, if you look at the electricity meter at your home, if you want to buy electricity, you pay for electricity in kilowatt hour. I am specific with my writing. The kilo is a small letter, while the W is a capital letter, and you have the H to be a small letter. So this is kilowatt hour. So you pay for kilowatt hour. So 1 kilowatt hour of electricity is equals to how much? Now, this how much depends on the tariff class that you are. We have the residential, we have the commercial, we also have the industrial like tariff. So presently, I believe we are hearing about our electricity tariff will be increased, electricity tariff will be increased. And it has been increased, but there are a little going forth here and there about it. But initially, some years ago, maybe 1 kilowatt hour is 26 naira. But for commercial industry, they pay as high as 53 naira per kilowatt hour. So here we have 1,006 watt hour, 1,006 watt hour. If I want to take this to kilowatt hour, what I will just do is to divide it by what? By 1,000. If I divide this by 1,000, what do I have? I have 1.6 kilowatt hour. So if I have 1.6 kilowatt hour, so the question is, how much am I going to pay for this 1.6 I have consumed just using this light bulb? So what I'm going to do is, I am going to multiply this 1.6 multiplied by 53. That will be the amount I will pay to the distribution company. I believe where you are there, if you are in Ibadan, that is Ibadan Disco. If you are in Ogun, Ibadan Disco also covers that place. If you are in Lagos, we have two. We have Ikeja Electric, IKEDC, and we have Eco Disco. So these are the two electricity distribution companies that we have in Lagos. So that is what this is all about. If you have questions, drop it in the chat box. I will see it and I can talk about it as we move. So we can also see the other ones we have there. So we have refrigerator, 120, quantity 1, total power 120, daily hours of usage was 8 here, and we have 960 the daily energy. Now, if we go down, we can see different loads. But let me talk about load 3 and load 4. Now, this is a television. Television on is consuming 68 watts. I have one of that, that's 68. I'm using the television for 3 hours, that's 204. So it's pretty simple. Now, look at number 4. Television, still the same television, off, standby. Now, one of the ways to practice energy conservation has to do with strategies that you use to ensure that whenever you are not using electricity, whenever you don't need electricity, you don't use it. So for instance, look at this television. If you switch off your television, maybe by using the remote, there is a standby power consumption that the television will be consuming. Standby power consumption, because some devices, some electronic components, the capacitors, they save this energy. So it's still consumed. Yes, you have off the television by using the remote, but there's still a standby power consumption about 5.1. So, but when we talk about energy conservation has to do with taking off energy, no trace, whenever you are not using it. And one way by which you can do for the television is to switch off the television on the wall socket where you plug the television adapter. So with that, you are very sure that no energy is being consumed. So, but if you just take it off from the remote, there is still a standby power consumption, and it varies depending on the device, how efficient the device you are using is. So you have DVD player, home theater, and the case. So if you look at here, if you multiply all the total power, if you add them up, we have 1,164. So the total power is 1,164 watts. Put the unit, very important. Now we have the daily usage and we have the time. So by the time you do all this multiplication, the daily energy is 5,447 watt hour. 5,447 watt hour. If you have any question, please drop it in the comment section. So let me just stop for now, and let me hear from one of you if what I'm saying is clear, and if you want me to continue, just say continue, sir. So let me hear from you. 1 minute. Okay. Thank you so much. So let's move on. So now I'm going to open the second sheet, now. So for the second sheet, we have almost same, but with some adjustments. Because here I'm trying to introduce the apparent power and the surge power into this table. But before that, I need to explain what the power factor simply means. What the power factor. Okay, somebody is asking, Silas, good morning, sir. My name, okay, I want to ask if sockets left on consume electricity as much. Now, if you look at the table, it doesn't consume electricity as much, but it takes a little bit. That's why we say if you off it from the wall socket directly, then you are sure that you are completely saving energy. But if you just use the remote to take it off, then you have some energy also being consumed on standby. Okay, so yeah. So I want to explain briefly what the apparent power is all about. So let me explain here. Now imagine a cup of beer. Now you can look at online, YouTube, and search the beer analogy. So this we explain in good terms what the power factor entails. So the beer analogy, so let's say we have a cup of beer, or is a mug. Okay, so we have this. Now, it is called the beer analogy. So you can actually read more on that. You will see some little explanation on that. So we have the beer analogy. So what is it all about? So it's used to explain the different types of power we have. So now, if you buy a bottle of beer, I'm not paid by any of the brands, so I don't need to mention their name. So there is what you have here, and there is this content, you have here also a foaming part of this. There's a foaming part. Now, we have basically three types of power in electrical engineering. We have the real power, we have the apparent power, and we also have the reactive power. Now, this real power represents what you have inside of the core below the foaming part. That is the real beer, Abi, because that's the real beer. So that is the real power. Okay, Daniel Akobodu said, how about a socket with no device plugged to it but switch on? In that case, if you have a device plug, if there's no device plug, then no current is being drawn. No current is being drawn. You understand? It is when you plug in the device that current will be drawn. So no current is being drawn, then you leave it. I hope I answer your question. So you can only say power has been used when you have a device drawing current. Okay. So we have the rebia. Now, this is the foaming part. The foaming part that you have here is what we call the reactive power. The reactive power. Now, the Pythagorean sum of the real power and the reactive power is called the apparent power. So we have the apparent power is rated in VA, that's the units. The real power is in watts. And the reactive power is in what? VA, so small letter R, reactive. So the reactive sum of this, so this a Pythagorean theorem. So we can have what we call the power triangle, where this side is the real wattage, this is the apparent power, and this is the reactive power. So we have V square is equals to what? W square plus what? VAR what? Square. So these are the three types of power you have in electrical energy. So you have the reactive power, you have the apparent power, and you have the real power. Now the question is, I want somebody to answer this question. The reactive power, is it useful at all? Considering the beer analogy, this is the foaming part. For those who drinks beer, does this make any sense for beer drinkers? I'm waiting for you guys to respond to that.
Question.
Yeah. So I'm waiting for response. So you have this beer analogy like I've explained. This foaming part of the beer, is it useful? Because we have termed it as reactive power, we have the apparent power, we have the real power, which is the water, which is the content of the beer that you sip in. This is the foaming part that stays on your mustache. And you have the apparent power. So who wants to respond? Anybody? Anybody? Hello?
If the foamy part of the beer
Yeah.
That's the reactive power.
Yeah.
If it's useful.
Yeah.
No, I don't think it's useful.
Okay.
Because
Okay. Because of what?
Because it doesn't actually have beer content. It's just foam.
Okay. Let's ask the beer drinkers. Anyone? Thank you for answering that question. Let's hear from another person also. Anybody?
If you're using the beer analogy,
Yeah.
because the foam still comes from the beer.
Okay.
And like if you leave it for some time, the foam will like still turn to beer. Like it's the beer that turns foam to the. So I think it might be useful.
Okay. Yeah, beer drinkers are talking now. Another person, so that we can close this. Is this useful, the reactive power? So if we take it to a layman, the foaming part of the beer for beer drinkers, is that part useful at all? So if we understand these three types of power, it will make a lot of sense for us as we go forward. So that's why I'm trying to take it as easy as I can so that we can all digest this together. Okay, any other person want to explain?
Sir, I think it is useful.
You think it is useful? Okay.
Yeah.
Okay. So for beer drinkers, when it is on your mustache, you get this kind of satisfaction. Yeah. You see those old men, when they drink it, they have the foaming part all around their mustache and they are happy, taking their beer. Okay. So, but for us, relating that to power, is it useful? So like I've said, the real wattage is the power being used by your appliance, your light bulb, your TV. They need the real power, and that's why you need the real beer. Now, like somebody rightly said, if you leave this, it settles and it becomes part of the beer. Yeah, I think there are professionals who knows how to do that. So in electrical engineering, is it useful? Yes. It is also useful, but too much of it is not good. So same, if you have two foaming parts, that means you are losing a lot of real beer content. So too much of it is not good. Like in electric motors or in some other devices, it helps to create the magnetic flux to allow the drive for motion. So the reactive power is not so useless, so to say, but too much of it is not actually good. Too much of the reactive power is not good because it is used to overcome torque in most of the mechanical devices. So we need to understand that. So understanding this will help us. So if you have too more reactive power in the system, your power factor will be low. Now, this power factor has a formula. The formula is the real wattage divided by what? The apparent power. So this is the formula for the power factor. And the power factor is between 0 and 1, where the 1 is the unity, power factor at unity. But can we get power factor as unity? Because we understand that in electrical engineering, we have losses. So because of these losses, it is not possible that it's only in an ideal situation that you can say the power factor is 1, so today. But because when you are using electrical devices, there are losses. So power factor is between 0 and 1. You can have 0.8, 0.9, 0.7, 0.6. So going forward, we will talk about the effect of these power factors. If a low power factor, let's say 0.6, this is not so good for the system it means that you have more what? More reactive power in the system. More reactive power in the system. So if your power factor is low, it means you have, so most times we tend to move our power factor to unity. But I told you, unity will be an ideal situation, and you may not really have an ideal situation. So in this case, you have a situation whereby at least your power factor should be around, the DISCO agreed to a use of power factor of 0.8. So if you have 0.9 is good. If you have 0.95 is good, and so on. So, but the thing is, most of our inverters, if you look at them, except for good inverters, you will have their power factor to be close to, except for good inverters, that you have their power factor to be close to unity. Sorry for that. So like I'm saying, except for good inverters, that you have their power factor to be close to unity. So most of the inverters, you have 0.7 and the like. So we have to be very careful about this. So when trying to choose an inverter, always try to go for an inverter that has a good power factor. But the good power factor will always come at a cost. So now let's go back to our table so that we can see how we put that into our table. So this is our table once again. So we have the appliances. We have the quantity. So I label A, B, C, D. So we have the total wattage. So I have 3 ceiling fans. The wattage is 70. Total wattage is 210. That's 3 times 70. And the power factor I'm using for this device is 0.7. So I'm using 0.7 for all these devices. Now, the apparent power, don't forget, I explained to you that the apparent power, the formula is P VA equals watt, this volt ampere equals to watt over what? Sorry, yeah, watt over divided by what? Power factor. Because I told you that power factor is watt divided by VA. So if you do a cross multiplication, your VA will be total watt divided by power factor. So now we are looking for VA here. How do we get this 300? That is 210 divided by what? Is 0.7. So now this ceiling fan does not have a surge. The LED light bulb does not have a surge. The LED TV does not have a surge. Then the fridge has a surge. So what do we mean by the surge? So I believe you now know how we got 107, 204, and also 214. The hour of usage you already know, and the daily energy is now the VA now, not the wattage again. The initial, the first sheet, what I used was watt divided times 8 times the hours, and you have watt hour. But in this case now, because we've included power factor, what we now have is VA. So we are having VA multiplied by the hours now to give us what? VAH, which is also the daily energy. Hope you got that. So now, as we are saying, so we have our 300 here by saying 210 divided by 0.7. So how did we get this 642 as surge? So the idea of surge is that if you have devices that are inductive in nature, so we have different types of load. We have resistive load, capacitive load, inductive loads. Inductive loads are loads that have coils of wires or magnetism in them, coils of wire wounded round a magnet, like as in case of a transformer. They are inductive loads. So if you have an electric motors and some other inductive load, when you start them, or like an electric pumping machine, if you start that pump, you will discover that at first you hear a sound which shows that it's drawing more current at start. So the current drawn may be, maybe the normal current the pumping machine is using is 2 amps. But when you start it at first, it can take like, let's say 6 amps. And this 6 amps can be so short for like, let's say 0.5 seconds. So this means that that pumping machine is taking what? Times 3 of what? The normal current it's supposed to be using during normal operation. So because you put it off and you are starting it for the first time, it's taking 6 amps at startup. So that is the surge. So the surge current is about 3 times the normal. So we can say the nominal current, let me just say, like the IN is let me say times 3 of the nominal current is the surge current. Let me just use X here as surge. So if the normal current is 2 amps and it's taking times 3 of it to start, that means it's taking a current times 3 of its nominal, which is 6 amps to start. So that's the essence of the surge. So we are saying that this fridge is taking a surge power of times 3. So if you do 214 multiplied by 3, you'll be having what? 642. That means the surge taken by the fridge is times 3 of the normal power it's supposed to be using. So 214 times 3 gives you 642, and that is how we have 1070. If you multiply it by 5, no, if you multiply 214 by 5, you're having 1070. How do we use this surge? This is what I will explain later. But I want you to get the concept that we have introduced the apparent power, we have introduced the surge, and we can now see the effect. We have the VA multiplied by the hours of usage, that gives us the daily energy. So if you add up all the surge we have here, the VA, so what is this VA? Can somebody add it up? And this apparent, the daily energy also, I want somebody also to add this up for us. I want to be sure that you are seeing the screen and you are following me. So what is the total VA we have now? And what is the total daily energy that we have now? Are we together? Hello, let me have the answer in the chat box. So if you have questions, please drop it. Let me answer your question. Okay, thank you. 825 VA as the total apparent power. And we have the total daily energy to be what? Thank you, 4,126 VA. Oh, somebody say we are on it. Oh, thanks. Good. So we are trying to confirm 825 4126. So somebody said here is 825 VA and here is 4126. Okay, so I want to stop a little here and I want you to bring questions. Questions, please. Questions. I want more answers to confirm what we have been given here. So please bring the question. Okay, another 4126, that means this is correct. Let me see a double hand again for the total VA. Okay, thank you. 825 also is correct. 825 is correct. So I want to take some questions, please. I need some questions. If you can mute yourself, let's hear you. If you want to type on the chat box, please, can you go over the surge factor again and how we got a factor of 3? Beautiful. That's a very question, Abib. Okay. Now, so that it will, so on the, from the manual of the device, the device will always come with a manual. So from the manual, you will get this information about the surge power of the device. The surge power of the device will always be in the manual. So for instance, the surge power of this fridge is 642. That shows us that it is 3 times the VA of the fridge. So the surge power will always be on the manual. So, but most times you can have some surge as far as 5 times the normal power or the continuous power of the fridge. 5 times. So if the fridge is 200 watt, that means the surge power can be 5 times. But now we are having more energy efficient devices and the surge also is being looked into. Okay, so I believe I've explained that. So surge power has to do with the increase in consumption as a result of the composition of the device. In terms of what kind of load is the device? Is the device a resistive load, capacitive load, or an inductive load? And I said most inductive loads, for example, a transformer, you can see that it has coils of wire around a magnet. So these are some of the, and there are some devices also that have transformers in them and some inductors in them. So these form part of the inductive loads. And these devices can consume more current at startup when you start them than normal. And this surge power is for a short time, like let's say half of a minute, and it will go back to the normal power it is consuming. Okay, somebody say, can I explain for them practical implication and application of power factor? So for distribution company, if your power factor is below 0.8, now the maximum demand, there's a what we call the maximum demand charge. It has been taken away. But you have some countries that if your power, if the DISCO tells you that the power factor agreed upon for industry is 0.8, and if you are using power factor of 0.7, these things can be measured with devices. You are going to be charged for going below the agreed power factor by the distribution company. So that maximum demand charge will be put on you. So they charge as a result of you going lower than the agreed power factor. So, and sometimes you may need to correct the power factor at your facility. So you may need to use, some people use synchronous motors, some people use capacitor banks to correct that power factor so that you can raise it from 0.7 to 0.8 or 0.9. So that's what they call power factor correction. So it is always good for you to work with power factor almost close to unity, though you may not have an ideal situation. So power factor is 0.9, 0.95, 0.8 are still pretty very good. I hope I answer your question. Hello, are we together? I want somebody to unmute and say 1 or 2 things if you understand what we have been explaining throughout. Okay, if you are here, I want to hear from you. Are we in sync with you and the other participant also? Or what I'm explaining, you don't understand? Hello, I'm waiting. Hello. I want to be I want to be sure I'm in sync with you, that I'm not talking to myself.
Yes, sir. So regarding the last question, can you like explain what is the essence of power factor? Like the essence.
Okay, so because there are losses in system, and these losses can come in diverse form, like I explained the reactive power, there's nothing you can do with it. The reactive power will be there. And most times when these devices are being used for a long time, they become less efficient and they generate more reactive power. So when they generate more reactive power, it affects the power factor, which is a ratio of the real power usage and the apparent power. So it's like it's a ratio between the real power and the apparent power. So that's why I was using the beer analogy to explain. So you want to ensure that the power factor of your system is close to 1. Because if you have lower power factor, that means your system is inefficient. If it's a generator, that means you will be consuming more of diesel, and that is more cost to you. That means you are not efficient. Your device is not efficient. Instead of you to be producing more, you are now producing less and you are spending more. So can you see why your power factor needs to be closer to unity as possible? Did I answer your question?
Yes, sir.
Okay. Okay, so I quickly want us to do an exercise. I will leave this on the screen for like 3 minutes. You already have. So somebody say, how do you ensure your device is efficient? How do you ensure your device is efficient? Don't go, for example, you want to buy electric iron. Hello, are we together? You want to buy electric iron, and somebody is telling you, oh, let's go to Alaba. Yes, Alaba is the home of electronics. People buy a lot of things there. You can buy good ones and bad ones. And they tell you there is an electric iron rated 2000 watts. 2000 watts. What do you want to use 2000 watt electric iron to do when you can have more efficient electrical iron consuming 800 watts? Some pretty ones you have 1000, but some can consume 1.5. So why you yourself have to be energy efficient? You have to be go for energy efficient appliance whenever you are buying anything. Don't buy Tokumbo fridge. Don't buy Tokumbo devices. Most of these devices that they send to the country that are not useful for them, because they are trying to use energy efficient devices in their own country. They now bring all these Tokumbo things to, but because you know that it is very cheap, you now go for Tokumbo devices. But you have forgotten that you will pay more on electricity usage because of the power consumption. Did you get that? So it's basically a behavioral thing, so to say. Did I answer your question?
Yes, sir.
Basically now, I want us to now, we plotted a table, or you plotted a table last week. So basically, I want you to do this. Plot your own table now. That table you plotted last week, introduce the power factor, get the apparent power. Now, if you have a fridge, or if you don't have a fridge before, introduce a fridge and let the fridge be times 3 of the power you are giving to. Yeah, I am using 150, so you can use 120. You can have 120, 130, as the case may be also. So can we quickly do that? just 5 minutes. We'll use this exercise to wrap up. And in the next class, we will now use this table to size an inverter for a solar energy system. We will size an inverter, and I will tell you how to select such inverter. So this table now, I want you to introduce the power factor on your table, the surge power. Then I want to get the total apparent power, the hours of usage. I have my own on the screen, but you have to create your own. I just need like one person to do that and share with us, and we'll wrap up for today. Is that okay by us? I can't, it seems Ogechi want to talk, but I can't, the network.
Did not plot at all last week. So
Hello, Ogechi, you are saying something?
oh, I was saying that some people are just joining the class for the first time. They didn't plot tables at all last week.
Okay.
So can we like take this exercise you gave? Can we like take this exercise you gave us as an assignment and then go over it at the start of the next class?
Yeah, it's fine.
So
So
we can sit down properly with it.
yeah, so you have the table. I've introduced the apparent power,
That
surge power.
That didn't start at all.
What do you
That
say?
the
Hello? Hello?
I said that's for people that didn't. Hello, Engineer Abiodun.
Yes?
I said that's for people that didn't start with us last week, that didn't plot tables at all.
Okay. So basically what I will do is I will share this with you guys. So plot your own, look at the loads in your house. Look at the loads in your house, plot this table, then we can now be on the same page since some of you are just joining today. So plot this table, introduce the power factor, take as many equipment as possible. This is just 4. You can take up to 10, depending on what you have in your home. Then we all come together, then we now start selecting. So I will explain how to size the inverter and how to select one in the next class. Okay, so we can go over one response so others can learn. Okay, fine, good. So who is ready? Let's just get one response. If you have introduced your power factor and you've plotted this table, we are waiting for you. Share with us and let's learn from you. And everybody will then need to go plot his or our own. And I want the responses in the group so that we just take it further in the next class. So I will look at everything in the group, then I can make corrections so that you can look at it also before the next class.
See the screen.
With the table.
Yes, I can see.
So what I'm saying is duplicate this yourself. I have 4 loads here. Increase it based on the load you have in your house. Introduce the power factor. Calculate the apparent power. Get the total apparent power and the total daily energy. The hours of usage I have here is 5. Depending on the hours of usage you want to use, it can be 2, 3, 4, 5. So it's not necessary it should be 5. Maybe you on your fan 8 hours in a day, your TV 2 hours in a day. So play with the hours of usage, take more appliances, fill in the table, be comfortable with your conversion. Remember, I have put it there that the power factor is the ratio of the real wattage, which is the total power, divided by the apparent power. And if you are looking for the apparent power, if you cross multiply, as in mathematics, you will have your VA times power factor equals to what? Equals to the wattage. And if you divide both sides by power factor, then we have our VA to be VA equals to wattage divided by power factor. So complete the table and submit in the group. I want to see everyone work. I can always vet it before the next class. So Daniel, do you want to share, or we can wrap up for today and take it to the group? Anybody?
Yes, sir, I'm still on it, so I think.
Okay. Okay, so what I would say is let's wrap up. So let me just take feedbacks. If today you have learned one or two things, let me know. So let's take feedback. Daniel, drop your work in the group. I will look at it. I will share this Excel with you so that you can do your analysis with it too. So let's have feedbacks before we go today. Thank you.
Okay, and Engineer Abiodun, thank you very much for the class. I learned something about the types of power, reactive power, real power. Obviously, and then I'll go back. And then I learned something about such power and power factor too. Okay. I think I need to sit back with the workings to look at it properly to get a proper understanding.
Yeah, beautiful.
Or every other thing is clear.
Yeah, beautiful. Please do. Now you can see I'm trying to take this as easy as I can, and you can ask me questions, drop questions, I will attend to it. Now, please, why I'm doing this again is I am not, everyone can come into the solar energy world. So please don't allow anything to give you challenges. So just talk to me and I'm going to answer your question.